Welcome back. We're on segment 3 of lecture 2 on descriptive statistics. This last segment focuses in on tools that we'll need as we move forward into inferential statistics. And there's just a few important concepts based on the summary statistics and a couple of new concepts that will be important as we move ahead. So the most important concepts in this segment are, again, to think about the normal distribution and the properties of the normal distribution. I'll introduce a new concept, the z-score, and a z-distribution. I'll also talk about percentile rank. We'll cover a little bit of probability, just very, very basic probability, and that'll prepare us for inferential statistics. So first, let's revisit this normal distribution. So you know a distribution is perfectly normal if it has this bell shape and if it's symmetrical around the mean. So here's the mean. 50% of the distribution falls below the mean, 50% falls above. It's perfectly symmetrical. This distribution is also standardized into a z-distribution, which I'll get to in a minute. The point of this graphic is to show that if we have a perfectly normal distribution and it's standardized into z units, then we know a lot about the distribution. We know what percentage of scores fall in certain segments or intervals of the distribution. And that will be important as we move to inferentials. So let's go back to the body temperature example. And I could ask you, what's normal body temperature? For those of us who think in Fahrenheit, at least for me, 98.6 pops to mind. If you're used to Celsius, you might say 37 is normal. But that's if you use the oral thermometer. There are a few different ways to get body temperature, right? So there's oral, there's internal. But more recently, there's something that people in the medical field and hospitals refer to as the wand. So the wand is an infrared meter. They look something like this, and what a nurse will do is just wave it over the patient's forehead, and it will read out body temperature. There's actually research to support a lot of nurses' sort of anecdotal evidence that the wand tends to run a little hot. So it tends to give body temperatures that are a little higher than if you do it orally. So we looked at this histogram before. This is just a normal distribution of body temperatures. So it's relatively normal. But you can see that the mean is high if you're thinking of 98.6 as normal, right? 98.6 is down here. So it runs a little hot, but it does it for everybody. So it's just a bias in the measurement that's across the entire sample. So there are the descriptive statistics or summary statistics. The mean is 100.06, standard deviation of about 0.71. The point of this is we can convert those scores, and I'll refer to those as raw scores. We can convert those raw scores to z-scores. And z-scores are a standardized unit of measurement. So if we have things converted into z-scores, then everybody sort of has an idea of what the values mean. So it's like converting into a universal metric. And it's real easy to convert a raw score to a z-score. You just use this formula. So a z-score is just the raw score minus the mean over the standard deviation. So a very simple example, if you wave the wand over my forehead, you got my body temperature. Let's just say, by chance, it was the mean. So it's 100.06. That's a real easy calculation, right? I would do my body temperature, 100.06, minus the mean, happens to be 100.06, divided by the standard deviation. I'd have a z-score of 0. And that's true of z distributions. The mean is 0. We can take that z-score and then convert it into a percentile rank. And percentile rank is simply the percentage of scores in the distribution that fall at or below the given score. So what percentage of the distribution is below my temperature if it's 100.06? If I'm average, if my z is 0, well, 50%, right? I'm right at the average. If we're assuming this thing to be perfectly normal, then it's symmetrical, so 50% is below the mean. So if my body temperature is 100.06, my z-score is 0, my percentile rank is the 50th percentile. Let's make it a little more interesting. Let's say I was running a little hot. It's 100.77. Plug that into the z formula. It's still easy math. I did this on purpose. So now we get a z of +1. Well, what's my percentile rank? Well, if you're really good at doing integrals and calculating area under a curve, then you could do it by hand. What a lot of us do is rely on R software or what's called a z table or the z distribution to figure out what the percentile rank is. So again, I said if we can assume a normal distribution and we assume normalized scores, meaning z-scores, then we know what percentage of scores fall in certain ranges. So we know that 50% is below the mean, and we also know that 34.1% of the distribution falls between the mean and 1 standard deviation above. So what's my percentile rank for a z of +1? 84.1. So again, using basic calculus or what we call a z-table or the normal distribution. So the gist of this exercise is that you should feel comfortable converting scores. This is like high school chemistry class, right, where you have to be able to convert from raw scores to z-scores to percentile ranks and back again. Okay? You should just feel fluid in doing that. I want to introduce the idea of probability here just in a very, very basic way. We're just gonna skim probability theory for now. And let's just look at the probability of an event happening. We could characterize that as P of E. The probability of an event happening is the number of ways that event can be attained divided by the total number of possible outcomes. So say we want to roll the dice. I often use cards for this, but this is a nice big graphic. Say we just roll one die. What's the probability of getting a 6? Well, that's real easy, right? It's just there's one way that can happen. There are 6 possible outcomes, so the probability is 1/6. Okay, that's all we need to know about probability for now. What's interesting is when you combine the ideas in probability theory with what we know about the normal distribution, then you can start to engage in inferential statistics. And let me show you how we do that. So we know certain properties about the normal distribution, if it's perfectly normal and if it's standardized. So I can start to ask slightly different questions about body temperature. So now I could say, what if I just chose one student at random from all of you people taking this course? If I just chose one student at random from the distribution, what's the probability that his or her body temperature would be greater than 100.06? Well, how many ways can that be attained? Well, it's half the distribution, right? So it's just the probability of x being greater than 100.06 is 0.5. So we can now start to make probability judgments about where people fall in the distribution. Let's just do that again to make it clearer. So if I do it again, I choose somebody at random. What's the probability that his or her body temperature would be greater than 100.77? Well, that corresponded to a z of +1 and a percentile rank of 84.1. So the probability of x being greater than that would be 0.159, because 15.9 plus 84.1 is 100. Okay? Let's go one more standard deviation further. And if I choose someone at random and get this body temperature, they need to go to the hospital. So what's the probability that I have a healthy sample, right? If I have a healthy sample, what's the probability that I get somebody with a body temperature greater than 103? Well, that's really unlikely, right? That means this is not a normal distribution. That means somebody in the distribution is not normal. They're sick, right? They need to go to the hospital. What's the probability of that happening? Well, that corresponds to a z-score of about 4. That's way off into the tail of the normal distribution. So the probability of that happening is less than 0.01. It's extremely unlikely given the assumption that everybody's healthy. That's exactly what we're going to do in inferential statistics. We're going to assume a normal distribution with certain properties, and we'll assume certain values, like what's the mean of that distribution, and then we'll conduct, say, an experiment, and we'll measure the same variables again, and we'll see, do they still fall into that assumed normal distribution? If so, then our manipulation probably didn't do much. But if they shift the distribution to the extent where the probability of observing the outcome is less than 0.01, like the probability of getting a body temperature of 103 from a sample of healthy people, that's just really unusual. That suggests something's wrong, right? That's exactly what we're going to do in inferential statistics. We will calculate the probability of certain outcomes based on certain assumptions, and when we get a probability value that low, then we're going to wave our hands and say, whoa, something's up here. This is statistically significant, and that's where that comes from. But I'm getting ahead of myself. We'll get to those topics in not the next lecture, actually 2 lectures down. But again, let's just pause and say, is it safe to assume a normal distribution? Remember from the first lecture, we often don't know the population parameters. That's why we're doing the research. We're getting random representative samples from the population to estimate those population parameters. So we often don't know if our variables are normally distributed in the population. It's an assumption we often make. So we have to keep reminding ourselves that if we are making that assumption, we have to remind ourselves that we're doing it. And is that a safe assumption? That all depends on measurement issues. And so we're going to spend an entire lecture on measurement. And in measurement, we'll talk about what is the construct under investigation. So say intelligence is a psychological construct. How do we operationalize that is a phrase I'll use in the measurement lecture. That is, what task or test do we administer to get an intelligence score? All of those decisions contribute to whether we see a normal distribution or not. And that's difficult in the social sciences, particularly in psychology, where we don't have direct measurement of our constructs. But I'll save that for the measurement lecture. So to wrap up here, the tools that we need for inferential statistics are the normal distribution, knowing its properties, this concept of z-scores as a standardized unit of measurement, and converting raw scores to z-scores and to percentile ranks, knowing just the basics of probability theory, and all of that wrapped together will allow you to start engaging in inferential statistics. And that brings us to the end of Lecture 2.